Welcome to this presentation on advanced optimization and design of post-tension concrete floors. My name is Jonathan Hirsch, and today I'll be talking about optimizing post-tension floor systems. When I say optimization, I mean we're going to adjust the design of the post-tensioning in order to increase the efficiency of the entire floor system, so not just to minimize the post-tensioning. We're going to take a look at the traditional post-tensioning design process. Next, we'll look at why it's advantageous to optimize. We'll look at the optimization criteria and the entire process from start to finish. And we'll look at how we interpret the results of the optimization. And then lastly, we'll do a comparison of optimized designs versus corresponding manual designs. So the steps in the traditional post-tensioning design process generally consist of initially laying out some post-tensioning, and this is true whether you're using a 3D design program or a 2D strip program. In a 2D strip program, you would break the structure up into strips and then lay out post-tensioning in each strip and perform a design on each strip individually. In a 3D process, you could lay out all the post-tensioning in 3D, but you're generally still breaking the structure up into strips for design. The next step would be to iterate the tendon forces and drapes to find a satisfactory solution, and which is one that satisfies all the code criteria. For ACI, often the flexural tensile stress limits control. For other codes, there could be performance criteria such as crack widths or deflections that control. Once the final post-tensioning layout that satisfies all the code criteria is determined, we would then calculate the corresponding mild reinforcement, any shear reinforcement that's required, in addition to studded shear reinforcement or stud rails. These iterations are very time-consuming, so generally only a few alternatives are considered just due to the time and cost involved in creating each alternative. I want to take a few minutes to go through part of the traditional process just so we can get a feel for the iterative nature of this process. So what I have here is the RAM concept tutorial model. So this already has structural geometry, input, loads, and even if we look at the tendon plans, you'll see that I have some profile polylines defined which define the tendon drapes. So this is all already defined. And I want to point out that this tutorial model has been modified from the one that's distributed with RAM concept. Specifically, I have reduced the slab thickness and changed some of the manual tendons over to tendon parameter objects for the purpose of this example. I want to go through the process of actually laying out the tendons and then iterating to a final solution. So in this case, I'm going to go ahead and just start drawing the banded tendons in the latitude direction. And we won't worry too much about the actual quantity of strands at this point, and I'll talk about that more in just a second. But in this initial pass, we want to make sure we satisfy any spacing criteria as well as the minimum force. So this design is going to be done to ACI 318.14. So this particular code does require some minimum level of pre-compression and maximum spacing in one direction. Since this is the banded direction, we don't need to worry about the spacing in this direction, but we do need to comply with the minimum pre-compression. So what I would typically do in the design process for this code is to set the number of strands in this direction initially to satisfy just the minimum level of pre-compression. And then we'll look and see at that point, after we do an analysis, if we have any failed code criteria, in which case we can add post-tensioning to try to resolve those particular criteria. So in this case, we're going to now look at the perpendicular direction. In this direction, we do have to satisfy spacing criteria, so we'll set the spacing to 4 feet, and the minimum force that would give us the minimum required pre-compression of 125 psi here is 12 kips per foot. So we'll start with that here. We're just going to lay out a couple of different areas of distributed tendons. And then since we have this little sliver here, I'll go ahead and just draw a little band there that'll cover that area. And we'll just put a few strands in that. So with that, we can actually generate our tendons. We can take a look at our tendon layout that's generated. We can see that we've got coverage over the whole slab. We should have our minimum level of pre-compression already covered in both directions. And so we can actually run this. And see if we have any criteria failures. So if we look at the overall design status, we'll see that we have quite a few criteria failures. These are all the flexural tensile stress limits. So what this is telling us here is that we're going to need more post-tensioning to create even just a satisfactory design before we can even start thinking about the economy of the design that we've produced. So in this case, the approach that I've traditionally adopted is to provide just enough post-tensioning to just satisfy these flexural tensile stress limits with the idea that the minimum amount of PT would be the most economical solution. So we'll take a look later at whether that's actually a good assumption or not. But for the time being, we can also take a look at our actual stresses versus those limits so we can get an idea as to how far outside of the bounds we are. We can see here that we've got a top stress failure in addition to several bottom stress failures. But this process is somewhat iterative, so we're going to have to basically come in and change the quantities of these strands, and we'll just kind of bump them up a little bit, taking a bit of a guess. Could spend some time trying to come up with some more exact increased numbers, and sometimes that might make sense. In this case, since we just have a few strands, we'll just bump them all up and run it again, and this model runs relatively quickly as well. So we can now see that we've resolved some of our failures, but we still have some failures that remain. Rather than going through this entire iterative process in real time, I'm going to speed up the video for the rest of the process, but we will go through the entire process from start to finish. And it really just requires continually changing, updating the tendon quantities, potentially profiles, running the model, and then evaluating the impacts on stresses. So I'm told by engineers that this process on typical size models can take 4 to 8 hours for a single design just to iterate to a single satisfactory solution. So you can see here that we have to go through the process in both the latitude and longitude directions. So we're changing the banded tendons quantities as well as the distributed tendon quantities, and we'll just continue to iterate and run the model. You can see we're down to a final few failures here. One of them is a stress concentration around the opening there, so we can add a few banded tendons there to handle that stress concentration. In this particular model, these iterations took about 10 minutes, but again, this is a very small model and it generally takes much longer on typical size models. But ultimately, after some iteration, trial and error, we can eventually arrive at a final solution that satisfies all of the required code criteria. Okay, we can see here now that we've actually resolved all of the failures. And if we take a look at the top stress plan, what we want to see to know that we've minimized the PT is that our tensile stress limits are close to the limits here, at least at most of the locations. You can see that we've achieved that here. We have that here. So it looks like in general we've got that covered. We've got both of our tensile stress limits in this bay right at the limit. So here, recall that it wasn't the top stress that was controlling, it was the bottom stress, and our bottom stresses here are still at that limit. So we've got 343 versus 379. So all in all, from the standpoint of achieving the minimum amount of post-tensioning that satisfy the flexural tensile stress limits, this layout is pretty close in design. So last thing we'd take a look at is just to make sure our deflections are reasonable. We can take a look at our take a look at initial service deflection contour and make sure we're not overbalancing anything anywhere. We might adjust a tendon profile there and take a look at our service level deflections. But all in all, we could call this design good with this level of post-tensioning. But the amount of iteration that's necessary to accomplish that is just really large and also very time consuming. And this is on a very tiny tutorial model. So on a larger model, a normal size slab, where you're performing this iteration over in a much larger scope, engineers are spending as much as 8 hours just performing a single design. So once we get done with that, we've really just still achieved a single design without any real feel for how economical that design is. We know we have a valid solution, but now we could spend more time trying to explore different solutions, but the process itself is so costly that that's generally not done. And so before we move on here, I just want to take a quick look at let's take a look at our estimate with our total costs. And this is based upon the materials that are in the model and the input unit costs that have been set here. So we have a post-tensioning cost, a mild steel cost, and then also we have some stud rails that were required. We could take a look at those here as well. We've got stud rails at several columns. And so this is a summary of our costs, and later we'll compare this to what happens if we run it through our optimizer. Okay, now that we've seen an example of the traditional design process, let's take a look at why using an optimization process might be advantageous. First of all, an optimization process that generates alternatives automatically can explore many different alternatives simultaneously and do a side-by-side comparison of those alternatives to determine which one is the most advantageous. It also can solve for the code criteria in the process, so all those iterations that had to be performed in the traditional process can now be performed automatically by the optimizer, so that the engineer doesn't have to spend the time changing all those values and evaluating the impact of that manually. It also allows for comparison of things like different tendon layouts and also even comparison of different slab thicknesses. And these are all side-by-side comparisons, so again, it's very easy to compare all of these alternatives in an apples-to-apples fashion. The optimizer works without the constraints that an engineer has in the way of intuition, so that an optimizer works with a systematic process to come up with the best alternatives, and it might result in alternatives that are not always intuitive to the engineer. And a couple of examples here, it might add some post-tensioning to remove mild reinforcement, and it might also adjust tendon profiles to balance the moments at the joints and decrease or eliminate stud rails. It also uses processing from cloud resources so that all of this work can be done in the background without interrupting the other tasks that can be done on the desktop at the same time. Now that we've looked at why using optimization can be advantageous, let's actually take a look at it in action. So we can look at the same model we were working with earlier, and you'll see that I have reset, so we've laid out the tendons just as we did in the previous example, but I have reset the tendons to their minimum values so that if we run this model now, we will get the initial code criteria failure that we saw initially. The point I want to illustrate here is just that we don't need to do all those iterations in order for the optimizer to work. The optimizer, as a byproduct of performing the optimization, will eliminate all of these failures and in essence automatically perform the design for us. So in this case, I want to take a look at our optimizable objects in RAM concept. So we have the banded tendon polylines, which have an optimization tab. And you can see that we can set a minimum number of strands, a maximum number of strands, and then the increment to explore. So in this case, we want to set our minimum number of strands to provide that minimum level of pre-compression that's required by ACI. And the maximum number of strands could be set to something practical. In this case, about 3 times the minimum is reasonable. But essentially, we want the optimizer to explore all the values in between as potential solutions. So that's what will happen here. In this case, so like I said, really what we want to do is set, in this case, our minimums to the minimum pre-compression values. In this case, we're going to increase the maximum of the range a bit, just to make sure the optimizer has plenty of space to explore. And the other thing we'll look at here are the profiles. So we generally don't change the high point profile elevations in an optimization. Those normally stay fixed. So we can actually turn on and off which objects we want optimized. So you'll see here for all of the high point elevations, I've deselected this checkbox, which means that we won't vary those, but we do want to explore changing the low point elevation. So we will change the overall tendon drapes, but we'll do it by leaving the high points fixed near the top of the slab and changing the low points to explore the variation of drapes on the tendons. So in this case, we just want to make sure that they have a reasonable space to explore. We could, if we know we have some long spans that are likely going to need lots of drape, we could limit those, but just to demonstrate that we don't need to do that, since we have an 8-inch thick slab here, I will set the entire range from 1 to 7 inches, and we'll put them into half-inch increments just for constructability. We might need to adjust this one a little bit because the slab is thinner over here, so we don't want that one to come up out of the slab. But now all of those ranges for each of these low point elevations will be explored by the optimizer. And we'll do something similar in the other direction. Again, if we look at the end elevations and the high point elevations, we've deselected all of those, so those will not be optimized, but we do want to vary the drapes for these low point elevations. And so again, we'll use 1 to 7 to give it the maximum space to explore. And we also might want to optimize the drape on this cantilever because it's controlled. It's a varying length cantilever, and we don't know how much might overbalance that cantilever, but we want to make sure we have enough. So we will give the optimizer an opportunity to change that one. Since that's referenced from the bottom, our maximum we want there is 5. And we know we probably don't want to go much less than mid-depth of the thinner slab, so we'll go down to 3 there. And we'll let that explore a few different elevations there. And we'll do something similar with the tendons then. So if you recall, we have these, we have added tendon here, and that's now set to 0. And we want to leave the minimum of that at 0 because we don't know if we need it or not, so we want to let the optimizer have the opportunity basically to eliminate it, but we'll also allow it to add a fairly generous amount of added tendon in there. We'll give that a fairly small increment. Let me get that. And I've added another one up here, again with 0 to start. And the idea here is that we don't know if we're going to need added tendons up here, but we want to give the optimizer the opportunity to be able to do that. Now for our main distributed strands, we need to make sure we provide the minimum effective force of 12, which gives us our minimum precompression. So our minimums here need to be set to that value. And again, we'll give this something fairly generous. Give it plenty of room to explore some larger forces. And that will cover the bulk of the slab. And then we've got these other banded tendons that were used to resolve isolated problems. We'll give this one, we'll set this one to a minimum of 4 and a maximum of 12. And this one is really just to fill a gap over here in the edge, but we'll also give this some space to explore. So we'll set this to a minimum of 4, a maximum of 8. And that's really all we need to do. Once we've set our ranges and we have our profiles and our tendon ranges set, that's all we have to do. We don't need to do any iterations. We don't need to actually resolve all these failures in it. The optimizer will take care of that. And so I'm just going to save this model, and then we'll click the Optimize Tendons button up on the RAM Concept toolbar. And we'll give this optimization a name. You can give it any name you want. It tells us how many optimizable properties we have. We're doing the whole slab, and we're going to optimize 28 different properties. Those are the ones that we've set to be optimizable on that optimization tab. And then basically we're going to give it some criteria which tell it when to stop. So we'll set this down to 1, and we'll set a maximum number of total 200 iterations. And then all we have to do is click OK to start this optimization, and that will start it up. As the optimization starts, I'm going to speed the video up here. We're going to be running thousands and thousands of concept models, and if we ran those in sequence, as you might expect, that would take a very long time, several days, potentially even several weeks. And by running these on the cloud in parallel, we're able to cut down that time drastically to generally several hours, but we want to speed that up so we can see a good chunk of the process here. Once the optimization starts, what's happening in the background is a genetic algorithm is intelligently and automatically selecting different trials, evaluating each of those trials, and then comparing them side by side. And so what you'll see is we have a graph that's being generated as the optimization evolves, which gives you the best trial at any given moment. So that as we look to the right on this chart, we expect the total cost, which is the y-axis of the chart, to be going down. While the optimization is running, we can also close the optimization manager window and continue to work on other things. We can minimize concept here and continue to work on other things on our desktop. Because the bulk of the computing is being pushed to the cloud, we're not tying up our desktop with all of these calculations. So you can even continue to work on another concept model at the time. At any given time, we can go back and reopen the manager window, select our scenario that we run, and we see here that it's finished. And now we have a number of trials which are sorted by the best trials in the lower table. We have our chart, which is now finished construction. You can see how the evolution of the optimization resulted in lower cost as we evolved. And so we can now select any of these given trials and load them into the model and run them. And we can see how that has now resolved all of the code criteria failures, which we see here in the window as well. We have 0 failures. And we have our total cost reported here in the table, which should now also match what we see in our estimate in RAM concept. So now that we've completed a full optimization, let's take a look at comparing the manual design we did with the final optimized design. So on the left here we have the original design that we did by hand, and on the right we will load one of our optimized designs. And as I stated, we can we can select the scenario we ran, and we have a table which now displays all of the different optimized designs that were created. So because we've chosen to hide ones with failures, the ones that are displayed are all valid solutions, so they have no code criteria failures. Some of them vary in the amount of post-tensioning rebar and stud rails. So we can choose the one that has the overall lowest cost, and that's what we'll do here and load that one. And we can just run this model. Let's just take a look at what our final tendon layout was compared between the two. So we can see for the banded direction we've got 12 strands versus 12, so very similar. Here we've got about 20 strands on the left, and we've got 24 on the right. 30 strands versus 30 strands. So they are very, very similar in the number of strands. If you look at the profiles, also very similar. Low points of 1 in all of the long spans. And the back spans have some slightly different profiles. One thing to point out here, though, is that while these designs look very similar, the design on the left required a great deal of iteration, and the one on the right really just required us to set the ranges, and then we let the optimizer do all the iterations for us. So it saved us all that manual iteration time. Let's take a quick look at the longitude direction. So again, we can take a look at this. We've got about 16 kips per feet here and 14 here. Here we've got 15.5, so a little less, and 14.5, so a little more there. So some slight differences here. Nothing terribly significant. And again, profiles very, very similar. As you would expect, we've got full drape in the longest spans. So some subtle differences, but nothing too major. Again, we needed to iterate all of these profiles and forces on the left, whereas we were able to just set the ranges on the right and let the optimizer do the work for us. So let's take a look at some of the performance characteristics of the two models. I'm going to take a quick look at the initial service. So this will just be at the transfer of pre-stress. See, we've got a little more positive deflection in this region, a little more camber in this cantilever on the optimized design. But all in all, this one is fairly balanced. If we look at the service load deflections, now remember, we didn't actually optimize for deflections. We were just looking at satisfying code criteria and reasonable range of tendons. So in this case, it looks like our optimized design actually minimized the deflections better than our manual design. You can see even in this cantilever region, we got a little more deflection in the manual design than we do in the optimized design. And we have less maximum deflection in the optimized design. So slightly better performance from the optimized design. We can also take a look at the total reinforcement. Let's just look at the top bars first. And I expect these will be fairly similar. And it looks like they are. And let's compare the bottom bars. We might see some differences in the bottom bars. And we do. It looks like the optimizer has eliminated bottom bars in several locations, or minimized. Definitely less bottom steel in the optimized design. And lastly, let's take a look at the punching shear reinforcement. And we'll see that the optimizer actually eliminated the punching shear reinforcement at this interior column. And if we look at some of these other locations, we'll see that the reinforcement itself was minimized. So here these rails have 10 studs on them, whereas the manual design had 15 studs. So we were able to reduce the cost of our studded shear reinforcement by eliminating a column in one location and then minimizing the demand, which spaced out the studs and requires less studs at other locations. And lastly, we'll just take another quick look at our estimate just for comparison purposes. So this design had a little bit more PT, the optimized design, which is likely why it was a little better in the performance characteristics and service deflection. And it did so in order to eliminate some mild reinforcing costs and also some SSR costs. But I want to point out here that the total reinforcement cost for the optimized design is more than 7% less than the total reinforcement cost for the manual design. So we've seen that the optimizer can produce a better design than we were able to produce manually. And we've also seen that the optimizer generally results in practical designs, including for deflection control. But we also just looked at a fairly small model, and you might be curious about whether or not the solution scales to larger models. Well, we've actually done some initial comparison studies with some various size models. You can see here that we've got eight different models that were all user models provided to us, so they contained user designs that we were benchmarking against. And you can see that we have displayed the comparison between the PT, rebar, and punching shear reinforcement. And we're looking at the percentage of the optimized values versus the original design values. So you might see that some of the post-tensioning values are smaller and some of them are larger. And the same with the rebar and the punching shear reinforcement. We shouldn't be too concerned with the values of the individual quantities, because the optimizer, as I said earlier, is really working to optimize the total cost. So if we look into this column, which contains the total cost, we'll see that the optimizer is always producing a better design than the manual designs. And we see that we get some models get better economic performance than others. We have an average savings of 15% of total reinforcement costs, so that includes the PT, rebar, and punching shear reinforcement. But we can see here that the optimizer is doing a good job of creating savings and value in our models and coming up with efficient designs. We can also easily perform comparisons of things like different slab thicknesses. So this is actually a podium slab where we were curious about comparisons of the results that we might obtain from looking at different thicknesses. And in this case, we've looked at several different thicknesses and plotted them side by side. To do this by hand would have taken likely more than a week of engineering time of iterations and producing these results. Whereas with the optimizer, I was able to simply change the slab thickness in the models, adjust some of the ranges slightly, and then start a new optimization. And the prep work to get these optimizations ready to run took less than about 15 minutes. So there was a huge savings in time in able to produce this sort of chart, which also creates an enormous amount of insight. So we can see from looking at this chart, we're looking at individual costs plotted near the bottom there. So we've got concrete costs, which are increasing linearly, which isn't surprising. Our PT costs tend to go down as the slab gets thicker. Our rebar costs stay fairly constant, and our punching shear reinforcement costs go down as we thicken the slab as well, which is also no surprise. But the most interesting part here is the total cost plot, where we can see this dip in the plot, which indicates the lowest point in this plot is actually the most economical slab thickness, which here is 10 inches. And there certainly could be some performance trade-offs as we move to a thinner slab in the way of deflection, and obviously we're getting more punching reinforcement. But it just provides a way to very rapidly and intuitively evaluate a side-by-side comparison of different slab thicknesses. So to summarize what we've looked at today, optimization eliminates many hours of manual iteration. In a sense, it performs an automated design, so it automates the design process and eliminates the need to go through all those iterations manually. And it can compare thousands of alternatives side by side, which is really the only way to know if you have the most economical solution. It also allows for direct comparison of different systems, such as different slab thicknesses, potentially different tendon layouts. And it very intelligently and automatically selects the trials using genetic algorithms, and that really provides for a hands-off design and optimization process. So you're not required to be watching it while it goes on. You can be doing other things. You can start it at the end of your workday and come back and review the results when you come into the office the next day. It also pushes the bulk of the processing burden to the cloud, so it keeps your computer free to do other things while the optimization is underway. Lastly, we want to show a location where you can find some more information. This is our RAM Concept PT Optimization landing page on Bentley Communities, and so we have a link here. And please check back here frequently as we will post our updates and information regarding PT optimization here.